Werner earlier mentioned the Boeing 777. A lot of my friends at Boeing say that the 777 is 8 million computer instructions flying in close formation. In fact, some of the system engineers there say that the 777 is a wonderful computer system that uses an airplane as a peripheral device. So that's the challenge we have today. More and more things have just become peripheral devices for the computer system that runs them. Now, the problem with being in test or quality assurance is that you know the truth, right? Because you see the dirty, ugly stuff that we're about to put out there, and you know whether it's good or whether it's bad. In fact, I'm going to redefine productivity with some of the problems that you know about that are going to kind of refine the way we think about how we actually measure it. Typically, you measure it by the volume of things you produce, the number of function points or lines of code or whatever your size choice is, over the amount of effort you use to develop it. And that's the normal way to do it. And I'm going to argue, however, that productivity is actually a monotonically decreasing function. And I'll show you why in a minute, unless you do something to stop it. Right? So most people want to believe that productivity is a nice baseline and it's steady from release to release to release. And we have this nice baseline and everything will be the same. Right? Now, that's true as long as the software you're working on is essentially the same from release to release to release. But we know that's not true. In fact, since the 1970s, we've known that over time, the quality of software degrades. The more we change it, the more we modify it, the more we add new functions to it, the architecture starts to degrade a little, the code gets more complex, and it becomes harder and harder to work with, and that's what causes productivity to be a monotonically decreasing function, unless we do something about it, right? Which means that we have to allocate time to go in and fix the problems that cause the degradation of either the architecture or the quality of the components themselves. Somebody's calling you. I mean, it's very simple to sort of think about what goes on in development, right? I develop some software, or my team develops some software. We make some mistakes. We spend about 40% of our time reworking them. In fact, for a low maturity organization, the data is pretty consistent that they spend somewhere between 30 and 50% of their effort reworking the code, fixing mistakes and having to retest and what have you. And typically the average is about 40%. Right now, they can't fix everything that they do wrong. So some of that gets moved forward to future releases. Some of it you'll never fix because it's not that big a problem, but some of it you know you have to fix. It's either degrading the architecture or it's a major risk to the operational performance of the system. So that moves forward. We move that rework forward to the next release, which is kind of cheating in productivity terms, right? Because that's rework I should have done on my release, right? So, and then on the release after that, right, I create some new defects, some of which we fix, some of which we don't fix. I'm not going to fix all the defects that had to be fixed from the previous release, so we just move all that to the next release. And this goes on and on and on throughout the lifetime of a product. And so the proposal is that we not just compute productivity as the amount of stuff we produce divided by the number of hours or the number of days it took to produce it, but that we actually adjust that by the technical debt we've moved forward. Because basically there's effort I should have spent on this release that I chose to push to the next release and let somebody else do it. So I get credit for high productivity because I just didn't go fix everything. I didn't spend all those hours required to clean up the mess that I made. Right? We teach our children to clean up their mess. We just don't always do it in software. And so we ought to be able to, if we can measure what we'll call technical debt, and I'll give you a description of that in a minute, we ought to be able to use that estimate to adjust the number of hours we really should have spent in this release to get a truer idea of what our real productivity is. It will give us a better predictor of what our future productivity will be, and it will give give us a better idea of what our lifetime productivity would be on an application. So there's three, there's three kinds of things we should measure with technical debt. Number one, functional problems, right, the things you typically find when you're testing. Number two, structural problems, the things you find with static analysis and dynamic analysis and some of the other techniques for looking at the architectural structure of a system. And number three, as the system becomes more complex and harder to maintain, there's a penalty you pay. It's just harder to work with. And you're going to have to subtract that as well. It's just taking more time. In fact, studies have shown that 50% of the time maintenance engineers spend trying to work on the code is spent trying to understand what's going on in the system. Not designing a change, not implementing a change, not testing a change, just trying to figure out what this mess is so that when I make a change, I don't have side effects that I didn't anticipate. And that's this third issue, right? As it degrades, it takes longer and longer to figure out what's going on. So don't worry about the equation. We have a white paper you can download from the CAST website that describes it, but we ought to be able to go in and look at the problems we know we have to fix, right? I may have 100 problems, but there's probably 30 or 40 we'll never have to fix, and there's another 20 or 30 that we might fix. But there's probably 30 we have to fix because they represent severe risk to business performance or they represent tremendous additional cost because they've severely degraded the quality of the application. So let's look at this concept of technical debt. You've probably heard about this. It was made popular in the Agile community. It was started by Ward Cunningham, one of the leaders of the Agile community, who said, you know, to get software out rapidly to meet the business need, we make a lot of decisions we know aren't right, but we have to do it to get the software delivered. And we know someday we're going to have to go back and fix it because it wasn't really a very good way to have built a particular component or to have architected a part of the system. And that's technical debt because someday in the future I'm going to have to pay to fix it, right? We're going to spend hours fixing that problem, and that's just a debt that we owe to make the system better. So we look at these structural problems, and there's two issues. There's what it costs me to fix the problem, and that's the principal of my debt. But as long as that problem is in the system, I'm probably paying interest. For instance, if it's a severe performance issue, then we're probably paying for cycles we don't need to pay for until that performance issue gets solved. If it's a maintainability issue, then I probably am taking a lot longer to work on the code than I would otherwise until I get that fixed. So again, that's interest on the debt until I pay the debt and fix the problem. To expand the financial metaphor a little bit further, right, there's liabilities, which are what happens when the system crashes. That's a liability. It's a cost to the business because the software failed. Or severe performance degradation, right, which cuts down the efficiency of the people that are working with the system. For instance, a 5% performance degradation in an insurance claim system being used by 1,000 claims agents is extraordinarily expensive. You cost that out, but the hourly wage and cut out 5%, it's very expensive. So this is liability. And then there's opportunity cost. The amount of time I waste fixing defects is time I could have used to add additional functionality that would have made us more competitive and could have gotten the new software into the business faster so we'd be more agile. So technical debt is a good metaphor, but it's only helpful if we can quantify it. And the nice thing is we've done some studies and shown how you can go in and quantify technical debt by looking at the number of defects you created that you know you have to fix, an estimate of the number of hours it will take to fix them. That depends on the complexity of the defect. And then what your hourly rate is for the people that will be doing the work. And you can get an estimate of what the technical debt is. It's frightening how large it actually is. It's enormous. And it can be a substantial portion of your future releases. So it has a huge impact financially on the cost of IT and on the total cost of ownership of a system. So I'm going to focus on the principle to some extent. But there's another problem. In the old days, one person could pretty much, if you really had a really smart designer or a really smart developer, they could understand the whole system because it was probably written in one language. You know, everything was written in COBOL back in the dark ages. But now that's no longer true, right? We might have a business system that's written in Java. So, you know, at the component level or the code unit level, I build my components. I run my unit test cases on them. I might use a freeware thing I pulled off the net to analyze the structure and do static analysis. And they end up looking pretty good. I've got elegant components. I'm really a brilliant guy, so I put them into the build. The next problem then is at the technology level, right, where my components, my Java components, have to fit with everybody else's, and it has to all work together, and just because mine were done right doesn't mean that it's going to interact well with everyone else's, because they may have different assumptions about how things should interact. Another problem we have with Java is that if you can spell Java with less than 4 A's, you're a Java programmer. My daughter programs Java. She's a visual arts major. She's an artist. Right? She has one computer science course, but she writes Java. So that's one of the problems we have, is that we're now so thin for the number of developers. We're bringing everyone in to try to build software, regardless of the amount of background they have in IT or computer science. Now, here's the bigger problem. Modern systems are stacks of technologies, right? We have the user interface level written in ASP or JSP. We've got the business logic written in Java or C++. We've got frameworks that are used with those, struts and Spring and others. We've got the data access. We're going, using SQL queries or some of the language to get to the data, which is stored in a database that may have its own language. We may be interacting with some ERP system that has its own customization language like ABAP. All right, and the worst case, if you're in a bank, you probably have to go off to the old COBOL mainframe system to get some of the data there. And the only place today they teach COBOL is in the Department of Ancient Languages over in the archaeology section. So this is the problem. No one can understand all this, right? We're at the point where to fully understand this, you have to automate. You really can't manage this kind of complexity because people are making assumptions about how their part interacts with some other part that's in a language or on a platform or in a framework that they're familiar with, but they don't know enough about. And they make assumptions that, well, maybe that has timeouts. Well, if it doesn't, you'll hang up all your threads waiting for a response that's never going to come, and it'll appear the system's crashed. That's a major reason that reservation systems go down, by the way. So this is an enormous challenge and requires that we be able to look at the entire system as a system, whether we're testing it or whether we're doing static or dynamic analysis, which is a challenge when this may be 4 to 6 different languages. So one of the things we're trying to do at CAST is give people the ability to look at the entire system as a system. We've got a technology that analyzes, or has parsers to analyze 28 different languages that are fairly typical in business systems, and a universal analyzers for those we don't have dedicated parsers for. And we take that parsed information and rebuild an abstract representation of the system so that we can see the data flows and control flows and object hierarchies and other kinds of architectural structures and functional structures in the system. And we've defined 1,200 violations of good architectural and coding practice that we go search for in that information. And those are in areas, well, I'll show you in fact what they're in. They're in areas like performance effectiveness, robustness, which is reliability, security, transferability, and changeability are both maintainability. So we really look for these different kinds of violations. For instance, in the security domain, we look for what are generally considered among the top 25 common weakness enumeration. There's a database that has this repository of the main problems in security. We try to catch all the top 25. Buffer overflows, SQL injection, functional injection, and what have you. So we provide data back to the executive at the sort of an overall measure of how good the system is. We provide the ability to the project or application manager to track trends over time in these different measures to see how they're doing. And we give a portal to the developers that they can say, if we have to fix this, where did that happen in the code? And it'll take them straight down to that point in the code and describe the kind of problem, and even has some information about how they might remediate it. So this is a system-level analysis, static analysis of the architecture and structure of a system. So it's structural quality as opposed to functional quality. Now, how do you manage this? I mean, because we typically think about managing testing and functional defects and fixing those, But people haven't spent as much time thinking about what do we do about structural problems in the system. Well, execs have to set policies first to make this happen. I mean, we knew that in the CMM. We know that in virtually any area, that if the execs don't care, no one's going to do a thing about it. So they need to have a policy about how we're going to manage the structural quality in addition to the functional quality of a system. People need to set targets for what are we trying to achieve? How maintainable do we need to be? How reliable do we need to be in terms of availability? What level of security do we need in this system? And that depends on the nature of the application. Then we need to find out what's the problem. You know, where are we right now? If these are my targets, where do I stand against those targets? And that means do an analysis, do a structural analysis of the whole system. And once we get that feedback, then we can plan actions for remediation. If you're in an agile environment, the biggest problem we have with dealing with technical debt is that marketing and the business always win over quality assurance people, which means that quality assurance may say, here's problems we know you must fix in the next sprint. And marketing and business come in and say, here's things that have to be done right now because we have competitive reasons to do it. Forget all that nonsense about maintainability. Get this stuff in the code now. And okay, so the backlog gets longer and longer and you never resolve the problems. That has to be a matter of policy. 15%, let's say, 20%, 10%, just pick a percent, has to be, of the stories have to be dedicated to fixing known problems in the system. And that has to be a policy. And unless it's a policy, you can never protect getting the technical debt resolved, getting these severe problems resolved against demands from the business for more functionality or from marketing for having neat new features they can advertise on TV. So once we do that, we go remediate the violations and test them and make sure that we've solved the problems. Management then tracks the results to make sure from bill to bill we're making progress against the targets that we set initially, and they report the results back to the business. And when you report them back, it's best not to talk about quality because the business doesn't understand the quality word. It's best to talk about the amount of reduction in risk for outages, the amount of reduction in risk for security breaches, and other kinds of things that they worry about and that get the CIO very upset when they happen. So this is an example of a telecommunications company that worked very hard on this problem. That are one of the larger telecommunications company, and they started using the technology to control the quality of what they were, because they had too many outages, the cost of ownership was going up dramatically. And as they started getting the data and feeding that back to the development teams, lo and behold, the number of defects started to drop. In many cases, we found that the developers weren't even aware of some of these system interactions that were causing severe problems. And we had to make them aware through feedback from the structural analysis at the system level. So there's a lot of learning that goes on when they get this. The worst practice in all of software measurement is to use this kind of information for performance appraisals, or to compare people and then give out rewards. They'll just, developers are too smart. They'll figure ways around it and they'll trash the measurement system. So the important thing is to use this for continual improvement within an application. That's the single most important, because that will reduce the cost of ownership and reduce the risk to the business. So people are starting to see these numbers in contracts. In fact, outsourcers have started to see people put numbers for structural quality, for security, for reliability, for maintainability into their service level agreements and their contracts. And their problem is not that they don't know how to deal with that, it's that every customer has a different definition of the measure, and it was driving them crazy. So they went to the Software Engineering Institute and the Object Management Group and said, look, we need a simple measure that we can use across all of our contracts for each of these major quality areas. So we put together a consortium for IT software quality. We had 24 companies join. We began defining measures, and in fact, I'll show you the measures that they chose. They wanted a measure for automating function points because it was too expensive and too inconsistent to keep doing that manually. They wanted measures for reliability, performance, security, and maintainability. So we spent 2010 and 2011 in working groups with people from these companies defining automated measures for these. Function points has now been, the automated function point definition specification has now been approved by the Object Management Group. And it's going to be, in fact, CAST will have that available at the end of this month in our technology, and others will have it available soon. So that will automate function points. It'll make them cheaper, and it'll make them consistent. And so these go through the OMG process, and ultimately they'll use the ISO fast track to move over to ISO. But we have definitions on the CISQ website for the 4 quality characteristics for the violations that compose each of those, and we only chose the ones that the members felt had to be fixed. Not everything that's a reliability issue, but the ones you had to fix to reduce the risk of severe outages. So those are available. In fact, I encourage you to go to the CISQ website. Membership is free. We've gone to a sponsoring a sponsoring model. The current sponsors are CAST, Capgemini, and Huawei. We have others that are talking to OMG about joining as sponsors. For everyone else, membership is free. You can go to the website www.itcisq.org and sign up, and you can go in and get the standards. The standards are inside the members area. And we're now moving the quality characteristic standard forward with OMG to make that an OMG standard as well. So there's a lot of other, we have blogs, we have places for people to have debates and other kinds of issues. So I encourage you to join CISQ. What CISQ is trying to do is drive automated measurement and create specifications for automating measurement so it can become a more integral part of software engineering, of the development and the testing and the quality assurance of large software systems. Thank you.